So our first talk of the afternoon is Bill Duke, and he'll tell us about the distribution of closed geodesics on the modular surface revisited.
Yeah, I've been requested to end my talk after 50 minutes, so this may be a blessing in disguise. I don't know. Anyway, I wanted to say a few words about my experience with Peter. I was his third student at the Quran Institute. He was basically a fresh PhD when I became his student. When I think about that now, I wonder, what was I thinking, you know? But in retrospect, I mean, it was one of the best things that ever happened to me. I originally was interested in number theory as an undergraduate. I was at the University of New Mexico, you know, a hot spot of mathematics and number theory. But my mentor there was Reuben Hirsch. And he sort of persuaded me to think about going into applied math because the job market was so terrible at that time. This was a long time ago, 30 years ago. And so he was friends with Peter Lax, and he persuaded me to try to go to the Quran Institute, and so I did. And I showed up there, and I started to take courses in PDE, and then I took a course from Peter on complex analysis, and my life turned around. I was turned back to number theory, and I'm forever grateful for that. Another thing that Peter did is he introduced me to some other very important people in my life, like Henrik Ivanic. So Peter used to have a summer camp at Stanford after he left Courant and went to Stanford. And this was a fantastic thing. He would invite people, and we would, you know, give talks about whatever silly thing we were working on, and he would heckle us and make us not be afraid to make mistakes in front of people. Anyway, it was a great thing, but he introduced me to Henrik at that time. And Peter had gotten me interested in studying the works of Hecke and Siegel and Linnick and Moss, people like this. And I was working very hard on those things at that time. And I met Henrik, and Henrik at that time was working on estimating modular form coefficients of half-integral weight. And so I talked to him about this, and then I realized you could apply it to what I called hyperbolic distribution problems. So the distribution of CM points and closed geodesics. And so that was another, you know, very lucky and fortunate thing for me that I happened to be talking to Henrik at that time. And then we ended up working on things for a number of years. So as luck would have it, last summer I was working with Aslam Imamoglu and Toth, and I realized that there was a case of those original problems that I did that I had missed. And I was very happy to see this, and I want to tell you about that today. So a lot of this stuff will be very well known to a lot of you, so I'll do it anyway. And I'm going to use a chalkboard, so if I write too small, please groan or something. So the subject is all about binary quadratic forms. With integer coefficients. Yeah, this thing is amazing. So I'm going to assume D is a fundamental discriminant. So that means that it's a discriminant of a quadratic field. And I want to consider the quadratic forms, the binary quadratic forms of discriminant D. Since we're assuming it's fundamental, these are going to be primitive. And assume A is positive if D is negative. And this set, of course, is acted on by the modular group, PSL2Z. So in fact, I didn't leave myself enough room, but let's mod out by that. So this is a finite set. And the fact that it's finite is non-trivial. The number of elements in here is the class number. I usually denote H of D. And there's other invariants that you can associate. If D is negative, the number roots of unity in the field K. It's always called W, and so I'll use these things. Now, if D is negative, you can associate to one of these forms a point in the upper half plane. I usually call this a CM point, because it corresponds to a CM elliptic curve. And, well, so I do have some pictures. So it's interesting to plot them in the fundamental domain for the modular group. It's not very interesting when D is 4, you just have 1 point. But the minute D gets large, you begin to see some interesting patterns. So this is not too big. D is 51,000, minus 51,000. Once you get up to 940, the class number being 945, you begin to see more patterns. And you can imagine that it's looking like it's pretty uniformly distributed. And it gets more dense down toward the x-axis because the hyperbolic measure does that. And then so I went up high with a big class number so you can see this pretty clearly. And I decided to try to break Mathematica. And I actually succeeded, at least on my computer. So that's a pretty big number. Now, actually, I don't know how well you can see it, but if you look at that, you can see some very strange little patterns here and there, circular patterns that are funny. I think Steve Miller first showed me a picture like this and noticed these patterns. I don't think they're very significant, but they must be related to the structure of the class group. It could be interesting. Now, if D is positive, we have a different picture, more complicated. So now it's natural to associate to the form a closed geodesic in the upper half plane. So if you take the geodesic, so if Q, again, same Q, if you take this quadratic equation, that's a semicircle perpendicular to the x-axis. And if you mod it out by gamma, you get a closed geodesic on the modular surface. And the orientation is determined by an associated hyperbolic element, which is sometimes more natural to look at anyway. And you can explicitly give it in terms of the coefficients of the quadratic form and a solution to Pell equation. So this, the t squared minus d u squared. So this is equal to 4, and t and u are minimal, positive. So of course, you can write down the fundamental A unit in terms of t and u in the field. So this is the smallest unit bigger than 1 of norm 1. And if you plot these guys, it's interesting to look at them too. It's harder to plot them actually. So here I took D as 28. Even though the class number is 2, it's really just 1 because there's 2 geodesics running opposite of each other, covering the same curve. And you don't really see too much there. I went to a bigger class number, 4 times 787, same situation. The picture on the left just shows you how they seem to be getting less dense the higher you go up, and the picture on the right is showing a detail of that. There are these peculiar bands, which I haven't tried to understand either, and they seem to show up all the time too. But you might guess from that if you put a measure supported on these geodesics, they seem to be getting uniformly spread out with respect to hyperbolic measure. Okay, now the first issue that shows up is how many of them are there? And so let me just review for you the class number formula because it leads naturally into what I'm going to do. So that's very classical stuff. So it's natural to look at the Eisenstein series, well, really, which in the case of SL2Z is luckily enough, it's an Epstein zeta function. This makes life so much simpler in this case. because you can apply the Poisson summation formula to understand it. So it's a sum over m and n integers. And this is really a quadratic form to the minus s power in m and n. So I can express this in terms of the zeta, in terms of the Eisenstein series for the modular group this way, where this is the usual Eisenstein series. So we take the imaginary part and average over cosets modulo the translations to the s power. And of course, this thing has a nice analytic continuation functional equation, pole at 1. Again, it's a special case of a very general set of Eisenstein series, the simplest one, I think. But it's beautiful because it allows you to understand the class number of quadratic forms in an analytic way, which is so commonplace now that that fact is still pretty amazing to me. But anyway, if you take the quadratic field, you take its zeta function, you know it factors into an L function of Dirichlet and the Riemann zeta function. And you can also express it in terms of the Eisenstein series, but you have different expressions depending on the sign of the discriminant. So if the discriminant is negative, you simply sum up over these CM points the Eisenstein series. So I'll denote these sums that way. So that's a finite sum over the classes. So that's essentially Dirichlet. It's an expression for the sum over all the ideals of a given norm in terms of the Eisenstein series. In the case that the discriminant is positive, you can also do this, but you have to integrate over these geodesics. So it's a little more complicated looking. No one. Now you still have a sum over the classes, but in general, these seem to be a lot smaller. So if I denote the geodesic by CQ, this. And one thing about this, this measure is I like to write it this way. It doesn't look like, it turns out it's the same thing as arc length, but it has a nice effect that if you reverse the geodesic, you take minus q for the quadratic form, this automatically changes sign, so it doesn't detect the orientation of the geodesic. Okay, of course, if you look at the residue, if you know about the Eisenstein series a little bit, you look at the residue at s equal to 1, you recover the class number formulas. And you can write them in terms of the L value at 1. So this is the nicest case. When D is negative, you simply get a beautiful formula for the class number in terms of the L value. And you can express this in finite form, if you like. In the case when D is positive, you get this unfortunate looking, but actually extremely natural factor involving the log of this unit. And then this times the class number. Now, it turns out that this factor here, the log epsilon times the class number, is actually the length of all the geodesics together. And each one of them actually essentially has length log epsilon times a constant. So this is the total, you can think of this as the total length of the geodesics. You can think of this, of course, as the number of CM points. Okay, so if you want to know the number of points or the length of the geodesics showing up in a picture like that, it's given by this L value. And, well, I hope Siegel zeros don't exist. But whether they do or not, Siegel's brilliant insight was that you can still estimate this from below, albeit with a non-effective constant, or ineffective constant. So this is very nice, and it corresponds to the picture up there that, in fact, the class number is getting big, and the total length of geodesics is getting pretty big, relative to D. So given any positive epsilon, you have such an estimate, you can't give the constant implied by that symbol effectively because it depends on whether the Ziegel zero exists or not. But it's very useful because it gives you some hope for understanding more about the distribution of these geometric objects because in that picture up there, it's pretty long. You have to multiply this by d to the half to get the size of it. Okay. Now, why you get a different point of view, and this is kind of how I look at this stuff, because the Eisenstein series is not just an Epstein zeta function sitting there giving you this formula. It's also part of the spectral resolution of the Laplacian on the modular surface. And it gives you the continuous spectrum. So if you have a nice function, and I won't give you details about what that means, so the non-Euclidean Laplacian. So if f is nice, meaning, well, suppose it's really nice, compactly supported and smooth, then you can give basically a Fourier expansion. It's a spectral expansion of it. And this will involve an integral against the Eisenstein series of some transform, which I won't specify. But you integrate the Eisenstein series along the critical line against some kind of Fourier transform of your original function. And wouldn't it be nice if that were all you had to do, but no. There's also a discrete part, which I happen to be glad exists in this case, involving cusp forms, mysterious Moss cusp forms of weight 0. And you know, this is in general form is an L2 type of theorem, but it can be made into a theorem where you have pointwise convergence uniformly on compact subsets if you let f be nice. Okay, now how is that related? Well, what I think I'll do is I'll explain how the Eisenstein series really enters in. I think this is a natural way to do it. What it does is it controls the vertical distribution of these points, or geodesics. What I mean by that is if you look at in vertical strips in the fundamental domain, it's really the Eisenstein series that controls that because of its very definition. It's defined in terms of the imaginary part of the images. And so, for example, if you look, let me go back to CM picture. So back here, if you took, for example, the strip between 2 and 2.5, and you think that these points are uniformly distributed, you could use the Eisenstein series to count how many points are in a strip. Not only how many points there are in the whole fundamental domain, but how many points are in a strip. And, you know, it's not going to tell you what's happening down here because you cannot get to these points in a strip, because if you take a strip, you're going to include points here which are actually equivalent to points way up here. But the Eisenstein series does that, and it does it in a very natural way. So, well, okay. So let me show you how that works. Let's let phi 0 be smooth, compactly supported on the positive real axis, something like this. It's pretty vague. And let's make an incomplete Eisenstein series, something which lives in the continuous part of the spectrum, by doing basically the Eisenstein series averaging. It's convenient to take an inverse here. Sorry about this chalk. So if I call that little phi of z, well, this function is gamma invariant, and it really is constant on vertical strips. But we can use it to pick out a vertical strip if we want by choosing the phi correctly. Okay, and so if you sum it up over these points, let me assume d is negative. So if you sum it up over, say, the CM points of discriminant d, you can write this out Now that's what you want to control if you want to control how many are in this strip where the imaginary, or 1 over the imaginary part is in this interval. Well, then I can express this. What I need to do is I need to use the Mellin transform. So if I take the Mellin transform of phi naught, then I can express it in terms of the inverse Mellin transform. Sorry, I can express phi naught in terms of the inverse Mellin transform. Choose some constant big, if you like, and then you have the inverse Mellin transform. Now, this inverse Mellin transform is very rapidly decaying on vertical lines. So this integral is going to be nicely behaved. And I can use this standard trick from analytic number theory to express this sum as in terms of the Eisenstein series. So if I do that, let me just write it here. What do I get? I get 1 over 2 pi I and then I get a sum over the CM points of the Eisenstein series because the imaginary part is built into this function. So you just have to interchange the order of summation. I won't give you the details, but out pops the Eisenstein series. Okay, well, that means we have the class number showing up. But more than that, we actually need the sum of the Eisenstein series at all points on the critical line, not just at 1. So we use this formula up here to express. We use this formula to express that sum in terms of the L function of Dirichlet. And so what pops out of this is, if I call this S, an asymptotic formula for S. So what we get is we get a constant times the class number. And this constant is really the integral of this invariant function that we built with respect to the hyperbolic measure. And then the error term that you make, so what you do is typical in analytic number theory. You push the contour to the left. The nice behavior of this function here lets you do that, and you're going to pick up a residue at s equal to 1 from the Eisenstein series, from the Riemann zeta function here. But if you can push it as far as you want, but the smart thing to do here is to push it to the critical line. And, well, okay, so why? So what you get is this. You get d to the 1/4. You get an integral against the Dirichlet L function. And then up against this smooth function. Okay, well, now you can see for this problem, since we're interested in d being large, negative large, what you really care about is the size of this L function on the critical line. And that's where subconvexity becomes interesting with respect to the discriminant. So this is a famous result of Burgess, that you have a non-trivial bound. If you use the functional equation for the L function and Fragment-Lindelof principle, you get something where the term, you get d to the quarter here. And, well, unfortunately, that's going to be too bigger than this, possibly. So you need a bound that's non-trivial. And Burgess did this for us in the 60s. So he got 3/16, but I'll just say it this way. Anything better than a quarter is going to help you. So what this implies is that, well, this thing is going to dominate because of Ziegel's theorem. So this plus Ziegel gives uniform equidistribution in vertical strips. So I'll just say in Y. Okay, so that's very nice. You can do the same thing here. You can detect geodesics going into vertical strips this way. The Burgess estimate doesn't care about the sign. Now, of course, getting the best exponent here is a very important problem. And there's been progress. Henrik and Brian Connery made some big progress in this problem, getting a better constant here. Of course, we expect it to be Lindelof hypothesis. This should be epsilon. And that would follow if you knew the Riemann hypothesis for all these guys. So that should be true. Okay, well, to get the equidistribution properly, you want to have distribution in horizontal strips as well. And, well, it turns out for that, it's very natural to think that the cusp forms, which are part of the spectral resolution, that they're going to be important. And yes, indeed. So you have to also consider sums of the CM points or integrals of the cusp forms. Now, I first learned about this from reading a paper of Moss, who really developed theta correspondences a long time ago, and I think motivated by this, essentially by this problem. And yes, indeed, he was able to interpret. Well, if you look at this formula, where is it? So let me say it this way. If you have L 1/2 plus IT chi d, you can interpret this as a Fourier coefficient, well, part of a Fourier coefficient, but of a half integral weight Eisenstein series. It's more complicated than that, but this is essentially what it is. Because this led to lots of research in trying to get Lindelof this way. It's a very interesting idea, to use the fact that these L values are Fourier coefficients. But it turns out that when you do the same kind of summation or integration with respect to a cusp form, you also get half integral weight coefficients. And that's what Moss observed. But it turns out that, there was a wonderful refinement, I'll say, of Moss's theorem. It's due to Peter and Svetlana Katak, which is very useful for this problem. It makes everything very explicit. And so let me tell you what that says. So they also use the theta lift, but they make use of multiplicity 1 to get an explicit formula. So for example, if D is negative, I'm not going to give all the details, but let me give you. So this phi now is one of those cusp forms. Phi is a Moss cusp form. And, well, you assume it's a Hecke eigenform. Assume it's even. If it's odd, everything vanishes. And then you can express this in the following way. So this is if D is negative. 24. So they figured out which half integral weight forms occur. And, well, it could be a sum of them depending on how many guys are preimages of the Shimura lift. And you sum over those guys. It's a finite sum. But the key thing is you get the coefficients. Dth coefficient, and then the first coefficient. And I'll explain why you're getting this asymmetry in a second. So what this allows you to do in the context of this problem is to reduce the estimation that you need to get equidistribution to estimating this. Well, I haven't said what that is. So rho d is the Fourier coefficient, the dth Fourier coefficient of this guy. And this is weight 1/2. It's for gamma 0,4, weight 1/2. So what this formula does is it reduces the equidistribution problem to estimating this guy. And it turns out, well, once you've thought about these things for 30 years, you realize everything is parallel, right? And the Eisenstein series estimation has a complete parallel for the cusp form. And so you expect something like this should hold. Well, so yeah, and that's where Henrik comes in, because Henrik found an amazing estimate for sums of Kloosterman sums. So what you do is, I'm not going to go into details at all, but you express these guys in terms of Kloosterman sums. And then Henrik found a method averaging over levels that allowed him. Yeah, in this case, the Kloosterman sums are Salier sums that can be evaluated. So that allows you to go much further in sums of them. And Henrik found a way to estimate them non-trivially and to get a bound for this guy, which is sort of like the Burgess bound. And then there's a similar formula for the case when D is positive and you're integrating. Well, okay, so let's state a theorem. So like I said, Henrik didn't actually do this case, but I did, and this part is really pretty straightforward. Maybe not completely trivial, but it's really Henrik's idea is the key thing. And so the bound that you need here, and this works for positive or negative D. This normalization is kind of wrong, but, and I'm not even going to bother to tell you what delta is. I think it was 1/192 or something, but now I'm sure it's much better. The key thing here, and this made me very happy when I first realized it, is that it doesn't matter what it is. Henrik's was, but yeah. Oh yeah, the 1/192 was the subconvexity. You're right. Okay. He caught me. Yes, Henrik, what? Okay, Henrik, but we're not going to continue this argument, are we? The key idea was bounding sums of Kloosterman sums. But as I was saying, I mean, the fact that this is positive is crucial because the Siegel lower bound has to be beaten. So you can't beat it by something like a little o or a log. You have to actually beat it by a power for this to become useful. Okay, so I'll just say it this way. A consequence of this was the equidistribution of those points and geodesics. Okay, now this business has expanded tremendously since that time. One thing that you notice is that, well, for the Burgess bound, that's an L value. And even though this is a Fourier coefficient, it's really also an L value. So, but there's also a theorem of Waltz-Bourget, which allows you to relate the squares of half-integral weight coefficients to L values also. So this turned out to also be a subconvexity estimate. And this led to looking at other types of subconvexity estimates. This one is, in a sense, it's the simplest one beyond the Dirichlet L value because it is still a twist of an automorphic L value. But this has led to an explosion of equidistribution type results, including the quantum unique ergodicity, and there's others. So subconvexity was one thing that was somehow stimulated by this. Of course, originally this problem, especially in the case of D being negative, originally that was an observation of Linnick, that should be true, and he proved it under using an ergodic method, under a hypothesis on D that there's a fixed prime that splits in K. Recently, it's not exactly his method, but the idea of using ergodic theory was applied beautifully to this problem and settled it completely without any extraneous condition. And, well, you write their names down. Ergodic triumph. So this is Einsiedler. If I can remember everybody, Lindenstrauss. Philippe, three. Philippe Michel. And last but not least, Akshay. Yeah. So they, the tricky case is when D is positive. So for the geodesics, and they.
No, that doesn't work for the D negative. You're still in business.
Oh, of course I am. Because they don't get an exponent, do they?
No, they don't do the D negative thing.
Okay, well, I assumed they could. But
You learned something.
I have a lot to learn, actually, because I still don't really understand this. But it's definitely non-trivial, and it's not exactly Linux. It's way beyond Linux, as far as I can tell. My understanding of Linux is that he used small orbits in the class group, which is a very subtle thing. But I'm not even going to try to summarize what they did here, because I'll make a fool of myself. But this method is much more general in other directions as well. So they're able to get higher dimensional versions of equidistribution using it. So it's really important. Now, okay, so I haven't talked about anything new. So let me spend a few minutes to give you some new stuff. So you can generalize this whole setup where you have a genus character of the class group. So you replace this guy by the simplest kind of Hecke-L function where you have a real character of the class group. And it seems, when you look at this, you think, okay, it's nice. It's elegant, of course, but it's not very deep, a deep generalization. It does do nice things like, replaces that with another discriminant, makes things symmetrical. So if you have a genus character of the class group, I think this is a beautiful fact. I mean, essentially Kronecker, but if you factorize the discriminant into two co-prime discriminants, this parameterizes the real characters of the class group. But their signs can be arbitrary. They can be positive and negative. So for example, if D is negative, so this case up here, one of them is negative and one of them is positive. And you can refine this analysis and you can study the distribution of the CM points in a genus using these characters. If D is positive, it's a little different though. You can have one situation where both of the factors are positive. And that's very similar actually to this. But if there's a prime congruent to 3 mod 4 that divides D, you can have factorizations where they're both negative. This doesn't always happen. But nice things happen when it does happen because, for example, the orientation of the geodesics come in pairs now. They're not equivalent to their negatives in this case. But the genus character is negative on negative guys. So it exactly compensates for that. A lot of the things go through, but the uniform distribution interpretation is different in this case. And it's really very different. And so let me give you an indication of what it is. For one thing, the L value, you still have this, and I think this is due to Hecke. So actually, how much time do I have? I have 10 minutes. So let me write this down. This is a really pretty thing. So it doesn't look much different, but it has a big effect, actually. So what am I doing? This is theta. Sorry about all the formulas. But no, so now we're summing up over with this kind of genus character. So we're in this situation here. Okay, but now you take the derivative of the Eisenstein series. which is weight 2. You take the z derivative. This little difference turns out to be, so now I'll call it ds. This little difference turns out to be pretty interesting because now, and this really goes back to Riemann, you can evaluate this as a rational number. And it's got a beautiful meaning. So, so the L value in this case, and it's more convenient to write it at 0. Okay, so there's a functional equation. So it's a little bit more convenient to write it at 0. Well, first of all, you have factorization in terms of these. This is Kroneker's factorization. You have a factorization, so you have a product of class numbers. So this L value, which is associated with a real quadratic field, is in terms of imaginary quadratic L values, which is kind of cool. But also, you can express this. So, well, first of all, it's in terms of class numbers. But the really remarkable thing is you can express this in terms of Dedekind sums. So this is usually called the Rademacher symbol, this capital phi. And it's an integer, and you could write it in terms of Dedekind sums. It's really a remarkable thing because it's interest in it has actually gotten greater in the last few years because it was shown by just that it's the winding number of the associated closed geodesic that we're talking about. Well, each individual term is a winding number of a geodesic around the trefoil. If you lift up to the group modulo, lift up to the 3 manifold, which is SL2, PSL2R mod PSL2Z. So it's a very interesting integer, but it shows up here, but it's the sum of these guys. And when you sum them with this character, you get something that's positive. That's interesting, because this thing's not always positive individually. And also, it's big, because as long as one of these is big, it's big. Okay, well, what does it mean geometrically? And so this is the thing. So I'm running out of time. I won't write it down. Let me give you a picture and show you what it means. What did I do with it? What did I do with the clicker? Okay. Oh, I'm going backward. Okay, so here's the simplest case. This is when D is 12. So the factorization is -3 times -4. And there's just one little geodesic over there on the left. And what I've done there is I've labeled the regions that the geodesic cut the fundamental region into pieces. And the integers, for example, the 1 and the 2 and the 3, that measures the crossing number when you start at infinity and you cross these geodesics. These are all oriented from left to right. So the integer goes up 1, 2, 3. And I've mapped it under the J function to the plane so you can see it more simply. So these are the 3 regions it cuts it into. Now, it turns out that this number here is the area. When you count, it's the sum of the areas of these pieces counted with the multiplicity of the integer. Now, this was actually observed by a topologist, Danny Caligari. That's where I learned it from. He had a topological proof of this. And I was very curious by this. It seemed so bizarre. So I tried to find an analytic proof, and I was able to do it along the lines of this. But then I realized that there's more here. Because, in fact, if you can count the area, maybe you can understand the distribution of the measure that this determines. And so that's what we were able to do. We were able to extend this method to understand the distribution of the measure that you get. And I should write something down. How many minutes have I got? So this is really pretty recent work, so it hasn't been written up completely yet, but I'm pretty confident it's okay. So For one of these genus characters associated to the negative discriminants, you can associate a measure, which I'll call this. So this is an associated measure. It's easier for me just to describe it in words. It's exactly what I said before. So you count the regions that are cut, that this cuts it into with the multiplicity. Oh, by the way, so I ran into this on the internet. This guy was the coiner of the word topology. And if you look at this diagram, it's exactly the same diagram. I was surprised by this. 1834.
He invented the word topology.
Yeah. So he was a student of Gauss. But I tried to understand what he wanted to say about this, and I couldn't quite understand it. But it's the same procedure where you start on the outside with 0, and this curve has an orientation, and when you cross in one direction, you go up by 1, and when you cross in another direction, you go down by 1. So for example, that's supposed to be a -1. Anyway, I thought that was amusing. But here's an example where the orientation really does change. So the green guys are going from left to right, and the blue guys are going from right to left. So when you try to define this measure, it's always 0 high up. And then you have these integers going down. They're increasing because the orientation is positive. And then it can go negative. And in fact, I thought for a while that because of this, it would always be positive. But no. Even this one here can go negative. So it's a signed measure. But the theorem is that these become equidistributed. Well, that means if you take a nice function and you integrate against it, that this approaches the integral of the function. By the way, this d mu is the hyperbolic guy. This is as long as d tends to infinity through factorizations like this. Yeah, so what's interesting, and why I think it's pretty, but one of the reasons why I was excited by this is because it's sort of the missing case, because the half integral weight forms are weight 3/2 in this case. And they, as far as I know, they weren't used before. They're used in the sphere problem, but only for the holomorphic case. So they were there, and they're just waiting to be understood. And this is what it is. And the method, we're actually we're using a version of your formula, but we're proving it differently. We're not using theta correspondences. We're using Kloosterman sums. But now, I want to end with a question, and this is what I'm really working on now. This curve, I mean, this decomposition seems very mysterious. But what I think it is, actually, it's better to think of it in the group, just like it's better to think of the closed geodesics in the group. And then what we have is we have a curve bounding a Seifert surface. And then these measures are simply, if you have a geodesic Seifert surface, these are simply the multiplicity of overlapping. So there's simply a surface. So I think what's in the background is the uniform distribution of bounding surfaces of the closed geodesics in the group. And I don't know how to prove it yet. But if there's an ergodic method that will apply to this kind of problem, maybe it would make that natural. Maybe it's actually simply a lattice point problem. So don't beat me to it, because I'm still trying to learn. But anyway, okay, so I think I'll stop there.
So for the groups where those period integrals do not give you some L function.
Oh, I didn't understand that, please.
I'm sorry. So for some groups where those period integrals, like Wasserger formula, do not exist for the groups. How do you, for those cases, the subconvexity does not allow you to make equidistribution, right? You cannot go through the subconvexity always.
Yeah, I believe that.
I mean, how do you deal with that problem for those groups where this I mean, those period integrals do not give you L function?
I don't know. I mean, I have no idea. It depends on the situation. I don't know of a general method. Do you, Peter? I don't know. The nice thing about the subconvexity approach is it's very uniform. You know, you believe Lindelof. So, but you can have situations where Ramanujan conjecture is false. So if you put yourself in such a situation, maybe it's not true. So I don't know. I don't have a general answer.
Maybe he's asking in connection with this problem.
Oh, with this problem, it's not a problem. It's not a problem with this problem, I don't think. Although the proof that we give actually relies on half-integral weight estimates, but I assume it can be given as...
You're actually proving this in the first method, the old-fashioned method.
Yeah,
The
yeah,
original proof.
yeah. Yeah, my original proof included this case. But, you know, are you saying that you cannot apply subconvexity in the weight 3 hat? I don't see why not. I believe maybe in higher rank groups, but, you know, I don't know.
I mean, for suppose hyperbolic 4 manifolds, you are...
Sorry.
Okay, so that was fine.
Other questions?
I think there's a whole, I think that Shea is probably the world expert on theories. You should answer.
So just a kind of small question. When D goes to infinity, does the factor rate to the D1 and D2 have to also somehow both grow?
Well, one of them does.
But they don't both have to.
In fact, the most interesting case is...
But they don't. But one of them can be sort of stay small somehow, and that's the other one grows.
It's okay. I mean, it's really a really interesting case is when one is -4, and the other one is a prime congruent to 3 mod 4.
Mm-hmm.
that's a very elegant case.
Why do you say it's? Why is that particularly
because,
elegant?
for example, if the class number is 1, which probably happens infinitely often, you have these beautiful identities for the class number in terms of the continued fractions. It's an elegant case.
Any other questions? Okay, let's thank Bill again.